Hello students, today we will discuss about the NICOL PRISM. It is a device which is being used in the pathological microscopes in order to produce the polarized light. That's why it is used as polarizer or it is used as analyzer. When it is used as polarizer, it comes at the bottom. That's why it is otherwise called as lower NICOL. When it is located in the microscope tube in the upper part below the eyepiece, it is called analyzer or upper NICOL. And the main function of the NICOL prism is to produce polarized light. So let us discuss this. So it is a device to produce polarized light in pathological microscope. Its main function is to either polarize or analyze the light as polarizer NICOL prism or analyzer as upper NICOL through the phenomenon of polarization, producing only one set of E rays with elimination of the O ray components through total internal reflection. So this is the very property of the NICOL prism, and it only allows one set of light rays vibrating parallel to short diagonal of its round face, and the O ray parts are eliminated by total internal reflection. So how it is being prepared and why we take use of the calcite, that we will discuss. So this prism is named after William NICOL, who devised it in 1828. He is a physicist. He took the transparent white of calcite, which is known as Iceland spar, in order to make this prism. There are reasons for which this Iceland spar or the NICOL prism or the calcite is used to produce one set of E rays polarized and allowed to vibrate parallel to short diagonal calcite. So why this Iceland spar is being used to produce the polarized light, and why not any other mineral, that we will discuss. The reasons are the calcite is found to be available in clear, fairly large blocks or crystals because of presence of three sets of cleavages. The three sets of cleavages produce rhomb-shaped blocks, and they are easily obtained because of the presence of three sets of cleavage. They are not at right angles, but because of which they produce rhomb-shaped faces. That's why the blocks of calcite which are obtained, they are said to be rhombic pieces. And here we need not cut the blocks. Simply breaking through the cleavages will yield the blocks, and they are fully transparent. Light transmitted through the calcite is perfectly white or colorless because Iceland spar is fully transparent. When you talk about a transparent substance, it allows all the light to pass through without any absorption. That's why this transparent violet of calcite has been used to produce polarized light. And another reason is that the two refracted rays which emerge through double refraction in calcite or ice spar, they are well separated from each other, so that steps can be taken to eliminate one of them and allow the other set of light rays to pass through in order to produce the polarizer, or in order to produce the phenomenon of polarization, which can be fruitfully used in microscopes in order to produce polarization effect. So these two rays are well separated. They are well separated from each other, and it is because they have high birefringence value. The birefringence value for the refractiveness for O ray is about 1.65 and that for E ray is 1.48, and the difference is about 0.17. And this is a very high value, and because of this high value of birefringence, the two rays are found to be well separated from each other, so that steps can be taken to eliminate one of them and allow the other set of light rays to pass through, which can be fruitfully used for production of polarization effect. Taking the advantage of these features, as I discussed here, first is it is obtained in blocks, second it is fully transparent, third is the two rays which are produced from the passage of light through them, they are well separated from each other. So because of these features, a cleavage block of Iceland spar is used to be utilized for the construction of the nickel prism, and the length of this Iceland spar which is chosen for making the nickel prism is about 3 times as long as its thickness, and it is taken to prepare the nickel prism. Why such length is being chosen? Because the total internal reflection effect is to be effective, so that one ray can be eliminated. That's why the length is maintained so. After taking this block 3 times longer than its width, it is cut into two halves longitudinally by a plane which passes through the two opposite corners where 3 obtuse angles meet. So this is the corner, and this is the corner, and through these corners this plane passes and divides the calcite Iceland spar into two halves. Then these two halves are cemented by another layer of organic material, that is Canada balsam, having refractiveness 1.54. So they are cemented together to form this nickel prism. Before these two halves are joined together, the top and bottom surfaces of the rhomb-shaped calcite are ground down to give an angle of 68 degrees with the long edge in order to ensure the phenomenon of total internal reflection. For light rays, that is for E rays that are eliminated through this total internal reflection, and they are thrown to the sides of the prism where it is being absorbed by the black wall of the prism. So aim is to eliminate one of the light rays and allow the other set of light rays. That's why the Canada balsam layer is being inserted in between, so that the two rays which are being produced from single set of incident rays, that is the O ray and E ray, they are well separated from each other, and the Canada balsam layer is placed in such a manner that to it the O ray hits at an angle more than 77 degree, which is more than the critical angle, and that's why it is thrown to the sides of the walls of the NICOL prism, and it is absorbed there by the black wall, and the other set of light rays being parallel to the long edge, they are allowed to pass through. They are allowed to pass through the prism. So this is the mechanism. Now let me. So this is the calcite drum, which is 3 times length is 3 times. It is 1 time. So such a piece is being taken. The top surface is ground down till this angle with the short diagonal. This angle makes 68 degree, and in this condition they are cut into 2 halves. They are cemented together by a layer of Canada balsam having refractive index 1.54. So how it works? Let us see. Functioning, how it functions. An incident wave of their light entering into the NICOL prism from the bottom parallel to the long edge is oblique to the C axis and is doubly refracted, so that one resultant wave is found to be vibrating in a plane perpendicular to the C axis, O ray, and the other in the plane which passes through the C axis, that is E ray, and is perpendicular to the first plane. We know O ray always vibrates in the basal plane perpendicular to C axis. E ray always vibrates in a plane that contains the incident ray and the C axis. As here the C axis is oblique to the oblique, and it is oblique to the long edge, and light is incident parallel to the long edge. In that case, double refraction takes place. So the first vibration has a refractive 1.65 because it is the O ray which vibrates perpendicular to the C axis, and in other words the mineral has refractive 1.65 for that light O ray when the first vibration is considered. The second vibration has an index which lies between 1.65 and 1.48 because it is vibrating oblique to C axis and not parallel to C axis. If it will run parallel to C axis, it will have refractive index 1.48. It is vibrating perpendicular C axis, it will have refractive 1.65. As it is oblique, so it will have a range from 1.65 to 1.48. And the first is incident at the Canada balsam layer. The first wave, that is O ray, is incident at the Canada balsam layer at an angle 77 degree, which is greater than the critical angle for this wave, and therefore it is totally reflected away and is absorbed by the walls of the prism, which are blackened for this purpose. So we have the two rays. One is O ray vibrating perpendicular to C axis, other is E ray vibrating parallel to the vibrating in a plane that contains the incident ray and the C axis, and that ray is being allowed to pass through, and O ray is absorbed by the walls of the prism. So the other wave, which too has vibrations completely polarized, emerges from the prism and makes the prism a polarizer, a source of polarized light. It is the very function of the polarizer or nickel prism to produce polarized light. So it is the source of polarized light. So all light now emerging out of the prism are vibrating parallel to the short diagonal of the prism. That is short diagonal of the round face of the Iceland spar, and are travelling parallel to the long edge of the prism, so that they will escape from the top surface of the ray is being vibrating part of the short diagonal. Vibrating part of the short diagonal of the round face, they emerge. E ray. O ray is eliminated through total internal reflection. Thus, they emerge through the top surface of the prism, moving parallel to the long edge, and these are the sets of E rays which are fully polarized and are used to study the optical properties of minerals under petrological microscope. So this is the very use of the polarizer or very use of the nickel prism as polarizer or as analyzer in the petrological microscope. When both polarizer and analyzer are used, they are said to be in such a condition that their vibration directions are mutually perpendicular, and that is called the crossed condition of the microscope, where the analysis of the polarized rays are made. That's why the upper nickel is called as the analyzer, and these two nickel prisms are best used in the petrological microscopes because polarized light is required for the study of optical properties of rocks and minerals. Simple light cannot be used because light is required to be allowed to pass through different atomic planes of the minerals, so that how the light is controlled by the atomic planes of the minerals, that can be studied. That's why polarized light is essential, and this is possible because of the use of these nickel prisms in the microscopes. So this is all about the nickel prism, and thank you all for listening to this talk.